Hi everyone, my name is Saffron, and today I'm going to be presenting cryopreservation of mammalian cells using Protic ionic liquid solutions. You probably already know why cryopreservation is important, but let's recap. So cryopreservation is the process of cooling things down to really low temperatures so they can be stored for a long time. Now this is important for medical applications. For example, right now, hearts and lungs can only be stored for 4 hours. This means that about 60% of them get discarded before they even have a chance to reach a recipient. Similarly, blood products and many other cell types can't be stored. Now, cryopreservation could solve this. Cryopreservation allows long-term storage, which could potentially eliminate organ shortages and save hundreds of thousands of lives. However, you can't throw a heart into liquid nitrogen and expect it to survive. You have to include additives. So the reason that you can't expect something to survive when it's thrown into liquid nitrogen is because of freezing damage. And there are two main avenues of freezing damage. The first is ice formation. So you imagine shards of crystal ice piercing through a cell. It's almost universally lethal. And the other mechanism of damage is concentration of solutes. So you imagine as water is being removed into ice, the small amount of water that remains becomes more and more concentrated in these salts and sugars, and so that becomes toxic over time. And this is where cryoprotective agents come in. So cryoprotective agents are kind of like the antifreeze that you might put into your car. They prevent ice formation, and they act as solute buffers so there's not such a toxic effect. Most current cryopreservation protocols rely on the same two cryoprotective agents. That's either DMSO or glycerol. However, these two are toxic and they just don't work for many cell types and no organs at all. So the purpose of my research has been to look for new cryoprotective agents, and this has involved testing them for the three key requirements of a cryoprotective agent. The first is that it's able to penetrate the cell, and this is so that the agent can act intracellularly. The second requirement is that the cryoprotective agent is able to suppress ice formation. And the third requirement is that they should ideally be non-toxic. My research is predominantly focused on using ionic liquids. Ionic liquids are combinations of anions and cations, that is salts, that are liquid near room temperature. Now these are highly tunable because you can choose any anion and cation, and by changing either of those, you can actually change the properties of these liquids. So this research specifically looked at 10 different ionic liquids, which were composed of different combinations of the anions and cations shown in this table. So for example, ethylammonium formate or ethylammonium nitrate. Now ionic liquids are exciting for cryopreservation because they're known glass formers, so they're known to suppress the formation of ice crystals, which is one of the main leading causes of freezing damage, as I just discussed. The first thing I wanted to do was test the ionic liquid's ability to enter the cells. This is that first requirement of being able to penetrate the cells. Now this was done using Shrink-Swell experiments. So you observe the cell under a microscope and you add cryoprotective agent to the outside. Now this creates an osmotic imbalance which forces water to leave the cell, and so the cell shrinks. If the cryoprotective agent can't enter the cell, then the system stays in this state and the cell remains shrunk. However, if the cryoprotective agent can enter the cell, it will do so, which reverses the osmotic balance and forces water back into the cell, and so the cell swells again. Now this process is So this video shows this process in real time, or at least accelerated time. So you can see that when the cryoprotective agent is added, so that's sort of when the cells move around, that these cells shrink. And I just want you to focus on these two down here because there's a lot moving around. So this is the addition, the cells shrink, and then over time they swell again. So this is that process of the cryoprotective agent entering the cell and the cells returning to their starting volume. Now, quantification of this actually requires measuring the size of these cells at every single time point to get an indication of their behavior over time. So this is shown in this slide here. So you imagine I've extracted the frames from that video and then I measure the area of these cells at each time point. So in their before state, over their shrinking, and then as they swell again. And then I convert this area to a volume, assuming a sphere, and that gives me the graphs on the next slide. You can see that for phosphate buffered saline, the cells decrease in size and then stay in that shrunken state. Okay, now compare that to DMSO, where the cells shrink but then immediately swell again, returning to their original size. What this means is that phosphate buffered saline doesn't enter the cell, but DMSO does. And this is exactly what we'd expect because these are the control experiments. Now compare that to the results. You can see that for the ethylammonium ionic liquid, so this is the ethylammonium cation with different anions, that, for example, ethylammonium nitrate, the cell shrinks and it stays in its shrunken state. The same for ethylammonium formate, where the cell shrinks and stays in its shrunken state. Now compare that to ethylammonium acetate and ethylammonium glycolate, where the cells shrink but then swell again. So what this means is that these two, EAN and EAF, cannot enter the cell, but ethylammonium acetate and ethylammonium glycolate do. Now let's compare that to a case with the ethanol ammonium cation. So you can see it's got the hydroxyl group on there. So ethanol ammonium nitrate, the cells shrink and stay in that shrunken state, but ethanol ammonium formate, ethanol ammonium acetate, and ethanol ammonium glycolate all have evidence of swelling again. So that means that these three can enter the cell. Now I just want to highlight ethanol ammonium glycolate because you can see that there's huge error bars and the cell size just seems to be going off the charts. Now this is a toxic effect, so even over the short time course of these experiments, I could actually observe the cells dissolving in the presence of this ethanol ammonium glycolate. So what this means is that these volume measurements aren't necessarily accurate because the cells are literally dying as I'm watching them. Now, of course, this means that ethanol ammonium glycolate would not be a good cryoprotective agent because of its toxicity, but we'll get to measuring that in a second. And finally, I wanted to look at these two ionic liquids. So these have slightly more complex cations. And you can see that the cells shrunk and then they swelled again, but very slowly. So this means that these ionic liquids are somewhat permeable, but they take a long time. So to summarize all of those results, some of these ionic liquids are capable of penetrating the cell. So they meet that first requirement of a cryoprotective agent. Now the second requirement was the ability to suppress ice formation. And I measured this using differential scanning calorimetry. So this method involves heating a sample and comparing the amount of energy required to change the temperature of that sample to a reference. And that can give information on phase changes like freezing and melting. And what I found was that these ionic liquids will be able to decrease the freezing temperature. So pure water, using this measurement, the freezing temperature was of course near zero. But if you added just 0.6 mole of any of these ionic liquids, that freezing point decreased by about 6 degrees on average. Now you can see that the ethanol ammonium acetate caused a much greater decrease. It's probably because of complex hydrogen bonding interactions, but they're beyond the scope of this discussion. Now importantly, you can see that DMSO suppresses freezing by about 5 or 6 degrees as well. So this means that the ionic liquids were able to suppress freezing to the same degree as DMSO, which of course is very promising for cryoprotective applications. Alright, so we can say that the ionic liquids were able to suppress freezing and some of them are able to enter the cells. So they meet two of the requirements of a cryoprotective agent. Now that third requirement is to be non-toxic. Now I measured this by having my cells sitting in media, adding 0.6 moles of the relevant concentration of the ionic liquid, and then measuring the viability of those cells over time in comparison to a sample that hadn't been exposed to ionic liquid. And this is what I found. So you can see that the ionic liquids cause a decrease in viability quite substantially and much more than DMSO. So for example, after 1.5 hours, the DMSO sample was still hovering at about 100% viability, give or take biological error. In contrast, the ethylammonium ionic liquids viability had dropped to about 40%, and the ones with more complex cations had dropped even lower to about 20%. And by the time you've passed 24 hours, pretty much all of the samples exposed to ionic liquids were below detectable limits of live cells. Meanwhile, the DMSO sample was hovering at about 40 or 30%. So what this means is that all of these ionic liquids I tested are quite toxic and are in fact more toxic than DMSO. That's summarized on this slide here. Now this isn't great for the prospects of cryopreservation, but despite these toxicity concerns, I did want to test the ability of these ionic liquids to act as cryoprotective agents. And this is because of that tunability that I mentioned at the start. These 10 specific ionic liquids might be highly toxic, but the ability to fine-tune them means that we could perhaps design more biocompatible ionic liquids that aren't so toxic. So it wasn't time to completely discard them yet. So what I did was I followed the standard procedure of freezing these cells, which is shown here. But instead of using DMSO, I used ethylammonium acetate. And I chose that ionic liquid because it had the most promising properties. So it was the most permeating, it had one of the lowest toxicities, and it suppressed ice formation. So based on that, I decided to test that one ionic liquid as a cryoprotective agent for these cells. And this is what I found. So you can see that the viability of cells stored with ethylammonium acetate was almost as high as those stored with DMSO, at around 80%. Now 80% is actually a completely acceptable viability on thawing, and sometimes when I thaw these cells that have been stored with DMSO, I get 80% viability. So actually 80% is completely within what you'd expect for a standard procedure. And this shows that EAA, or ethylammonium acetate, can act as a successful cryoprotective agent, despite the concerns with its toxicity. So what does this mean? Well, firstly, I found that both the cation and the anion can influence permeability and toxicity, so it's important to consider both components of the ionic liquid. I also found that ethylammonium acetate can work just as well as DMSO for the cryopreservation of these cell types. I've also shown proof that ionic liquids can act as cryoprotective agents. Now, despite the high toxicity of these specific ionic liquids, as I just mentioned, the ability to tailor these means that there is actually millions of potential ionic liquids to be tested, and many of these would be more biofriendly than the ones that I've looked at. Now this is exciting because it might mean that some of these ionic liquids are able to store cells that we can't store using traditional methods. So that's definitely worth pursuing. And that leads me to my next steps. That's to test and make more biofriendly ionic liquids, and also to test ionic liquids with other cell types that can't be stored using traditional methods. Thank you very much for listening. Now this work has recently been published in JCIS, and if you have any questions about anything that I've discussed, please feel free to email me. Thank you.